Let's look at temperature and how it influences thermodynamics. Using this Gibbs Free Energy Equation of delta G equals delta H minus temperature times the delta S, and remember temperature is in Kelvin, we can see how temperature can change whether something will be thermodynamically favorable or not. I recommend that you know how to sketch this chart. So across the top, you are going to put negative delta H and a positive delta H. So this one would be exothermic, which can be a driving force of the reaction. And this one is endothermic, which is not favored. And then we have a positive delta S. This is an increase in disorder. And a negative delta S. So this is a decrease in disorder. And I know that a positive delta S can drive the reaction. So notice that when you have both that are favored, so both exothermic and increasing disorder, it will always be favorable. My delta G will always have a negative sign. And if you have the opposite, it will be never thermodynamically favorable. So your delta G will have a positive sign. And then we have an endothermic reaction, but an increase in disorder. This will work with high temperatures. So a good example of this would be boiling water. Turning liquid water into a gas is not thermodynamically favorable unless you're higher than 100 degrees Celsius. If that happens, then your delta G will be negative. Temperature is important. And notice that in this space, it's higher than the other one. So this means at high temperature, my delta G would be positive. And then let's look at a decrease in disorder, or making it more orderly, and an exothermic reaction. This means at low temperatures, you will have a delta G that is positive, and it will be thermodynamically favorable, but only at low temperatures. A good example of this would be turning liquid water into solid water or ice, and it would not happen at room temperature. The temperature is just too high. However, if I was minus 10 degrees Celsius, that's less than the freezing point of water, so it would be thermodynamically favorable for liquid water to become ice. So again, spontaneity can determine temperature, and this is the example that I was talking about. If the temperature is really, really low, it's spontaneous or thermodynamically favorable to form solid water or ice. And if the temperature is high, then that's not going to happen. So it's going to be non-spontaneous if you are at a temperature above 0 degrees Celsius. Pretend numbers into your Gibbs Free Energy Equation just to see how things work. So for example, let's say I have an exothermic reaction and I have an increase in disorder, and I'm just going to put in some fake numbers. So let's say minus 50 here, and I'm just going to keep my math really simple. So temperature is 10 Kelvin, and I have a positive 10, and I see that total I get a minus 150. And so I see that I always get a thermodynamically favorable reaction. It doesn't matter what my temperature is because there's a negative sign here. No matter what my temperature is, as long as my entropy is positive, I'm always going to get a negative number. So a negative number plus my negative number with my exothermic reaction, I'm always going to get a negative number. So therefore, it will always be thermodynamically favorable. However, if I have the opposite, so I have an endothermic reaction and I am decreasing disorder, and I'm just going to put in some fake numbers just so we can kind of see this. I see that I'm always going to have a positive number with my endothermic reaction. And then here, I'm going to have a negative times a negative. It's going to be positive. There's nothing here to make it negative. So I'm always going to get a positive number. So therefore, it will never be thermodynamically favorable. Delta G is going to be positive. So now let's take an exothermic reaction, and let's take a decrease in disorder, and let's look and see what temperature will do. My exothermic reaction, it will be negative. And for my temperature, let's do a low temperature. I'm just going to say 3. And my disorder is a minus 10. So overall, I get a minus 20. So it would be spontaneous at this low temperature. Now let's make the temperature go up higher. So we'll just take it to a positive 10. And so now I end up with a positive 50. If this number stays low, and because I'm going a negative times the negative, as long as it's a small number, then my exothermic reaction, whatever number that is, can handle it. So it will stay a negative, but as soon as that temperature gets high, then it's going to go into the non-thermodynamically favorable area. All right, let's look at this next one. So this is an endothermic reaction, and this is increasing disorder. So I'm going to put a positive 50 here, and then let's look at a low temperature and see what happens, and then a high temperature. So I end up getting a negative value here as far as my temperature and my entropy. But my endothermic reaction number is high enough that it still stays positive. However, if I have a high temperature, so I'm just going to take it up to 10, then I end up getting a negative 50 kilojoules per mole. With a high enough temperature, it will cross over and become spontaneous or thermodynamically favored. So let's do a problem where we're looking at temperature. So I do have the standard delta H and delta S and delta G, and that's all at 25 degrees Celsius, unless it doesn't change too much if I take my temperature up to 500 degrees Celsius. But let's use Gibbs Free Energy with this 500 degrees Celsius. So I put all my numbers down. Make sure you change that delta S to kilojoules. And my final answer, I get a positive 55.4 kilojoules. At 500 degrees Celsius, will the solid spontaneously split up into calcium oxide and carbon dioxide? And the answer is no. So this will not be spontaneous, or products will not form. So it's non-thermodynamically favorable. So I know at 500 degrees Celsius or 773 Kelvin, this reaction won't work. But at what temperature will it work? So to find the temperature it will work, I'm going to say that delta G is equal to 0. The solid doesn't become a liquid, instead it just decomposes. So let's look at a phase change when I can be at equilibrium with the calcium oxide and the carbon dioxide. So this will occur when delta G is 0. So if I write my Gibbs Free Energy Equation, and I know that G is 0, then I have delta H being equal to T delta S. I want to solve for temperature, so let's get temperature on its own side. And I get temperature equals delta H over delta S. And I know both of those values, they're given to me. And just make sure that the units match. So when I divide this number, I get 1,121 Kelvin, and I can change that to degrees Celsius. I get 848 degrees Celsius. So at this temperature, I would be at equilibrium, where that solid is hot enough now that it's breaking up into calcium oxide and carbon dioxide. So anytime you need to know the temperature of a phase change, you can use this formula. Put delta G to 0, and then find your T, or your temperature, equal to delta H over delta S. At what temperature does this reaction of ice melting into a liquid become thermodynamically favorable? And you might already know what temperature this occurs, but we can calculate it. So when we're at a phase change, that means we're at an equilibrium. And when we're at equilibrium, delta G equals 0. So if I have my Gibbs Free Energy Equation, and I make G equal to 0, and I can rearrange this and then solve for T, I have delta H divided by my entropy. And I just put those numbers in. Make sure your units match. And these are both in joules, so I'm okay. When I divide, I get 273 Kelvin, which is 0 degrees Celsius. So we anticipated that would be our answer, but this is how it can be worked out. So this is the equation you're going to use anytime you have a melting point or a boiling point. So let's do a problem where we put everything together. So first of all, it says find the normal boiling point for pure bromine, and we are given this thermodynamic data. So we have our delta H and we have our entropy. So I'm going to find my delta H by taking the products minus the reactants. Now I'm going to find my delta S. Again, products minus the reactants. My delta S is in joules, so I'm just going to quickly change it to kilojoules by dividing by 1,000. I know at the boiling point, my free energy will be 0. And if I take the Gibbs Free Energy Equation and I have delta G be 0 and I solve for T, I get delta H over delta S. And then plugging my numbers in, I get 330 Kelvin. So this is finding the delta H, the delta S, and then finding the temperature of that phase change. Now, predict the evaporation of bromine should be thermodynamically favored at 200 Kelvin. Confirm your prediction by calculating the value of delta G for this process of going from a liquid to a gas. And we're going to assume that our standard values of enthalpy and entropy do not change with temperature. So write the formula, and we will replace those values that we found before. Make sure that your temperature is in Kelvin, and then let's go ahead and do the math, and we get a positive 12.1 kilojoules. And because our delta G is positive, then we know that it is not thermodynamically favorable.